Today's episode is going to be all about experimenting with more particular sound effects that I can create, trying out new formulas, new techniques, and whatever. So, some of the previous episodes, or pretty much all of the previous episodes, have been about things I either understood or that were new to me but were very much related to computing related problems, things that rely on a programming skill set. But there's this thing I like to say to point out a part of what programming is all about, which is that you have to kind of know something outside of programming to actually connect it to anything real or useful in the end. You can spend all day learning languages and operating systems and computing things, but until you can connect it to something outside of computing, it is pretty hard for it to become useful or interesting in any real way. Of course, when you're on a team, it's a little bit more possible to contribute to just solving computer problems because you'll have other team members who can sort of help with that. So it's not that you can't be a useful programmer and only have, practice computing skills. But I think for me, since I'm doing this by myself, I have to do things that connect to outside of computing. So today I'm working on music and audio related theory stuff that is roughly way more new to me than what I should probably be at if I'm going to try to teach it. So this is not an episode in which I'm going to try to teach almost anything. Instead, this is more like you seeing my journey of trying to learn a new topic through the lens of me programming something about it. Since I don't know this super well, I can't really confidently teach it, but I can write code about it because I know it a little bit, and I've done a little bit of independent research to understand what I'm going to be doing today. And instead of trying to teach it, I'm just going to explain what it is I'm trying and how I understand it a little bit. And you should take this more as an example of what it's like to try to learn something using the computer as a tool to learn that thing. So the very first thing I'm going to do is this 12-tone pitch table thing. So I'll give a quick explanation of that. What 12-tone pitch is it's the way, like when you see a piano, it's organized into octaves, and there are 12 tones in each octave. And the way it works is you want sounds that are exactly double or quadruple, or like powers of 2, basically. If you take a frequency and you double its frequency, it sounds like very similar, and that's what an octave shift is. So if you have the C, note, and then you go up an octave on the keyboard to the next C up, the frequency of those two waves, the high one should be have twice the frequency of the lower pitched one, right? And so that's kind of interesting because it raises the question, how do you space out all the things in between? And the answer is you use this formula here, which actually kind of makes perfect sense. It gives you a smooth curve that grows exponentially for each half step up the piano keyboard. So I'm going to make a thing because I kind of want to be able to, without having to type in each frequency, I kind of want to be able to just say, play this combination of notes on this synth thing we've created, and hear the chord that creates. And I don't want to have to think about what the individual frequencies are when I'm doing that. So I kind of want to just have a table of those frequencies pre-computed so that I can rely on it when I'm putting things together. So I'm going to do that one first. All right, I had a lot of fun setting that one up. I thought I would just do the 12 equal temperament, or 12 tone equal temperament pitch table, and I ended up going a lot farther than that, but it was kind of neat. So the first thing I did was I set up a little system there to let me experiment with rendering chords, and I have a couple of insights about things I could do with the timeline system, that would make compression a little smarter, so that if there are lots of overlapping voices, the compression parameter goes up, and when there are only a few, it doesn't go up. Something like that might be neat. And then I also was thinking I could set up a slightly smarter system for how I blend things, and some ideas about how I separate out voices, instruments, the like sort of score, or like the sounds I want to send to an instrument. Like, I've got a couple of ideas there about how I could sort this thing out a little more when I want to start synthesizing like more musical kinds of sounds. So that was fun. And then I went and parameterized the pitch table, so it's not just 12-tone equal temperament, but I could set up any equal temperament based system. So I set up a 10-tone equal temperament scale and fooled around with that, and I ended up with a cool chord progression. So couple quick samples here. Here's what the 12-tone just normal C major chord sounds like. And then I was goofing around with the 10-tone equal temperament non-standard scale thing, and I came up with this chord progression that kind of sounds alright, I think. Anyway, that was fun. Next up, I wanted to play with the way pitch bends work. So I set up these little sine wave and other shape generators, and they have a built-in pitch bend, which is how I'm going to leave it for now. I think I could maybe like separate that out in the future, or do something more interesting with it, or more powerful with it, but I don't quite know how I want to do that. But one thing I want to try today is to experiment with the way that sounds. So what I did originally was I just put in 2 frequencies, and it linearly interpolates over the course of a time frame which frequency it's using. And based on sort of just that math I put on the screen a little bit ago, and my understanding now of how these normal tuning, the equal temperament tuning systems work, it seems to me like maybe you'll get a much maybe the sound you actually want is the one you get when you interpolate across a sort of exponential curve. So what I want to do is take the frequencies, take their logs, interpolate linearly, and then exponentiate them again, so that I still have the same endpoints and all of the midpoints are sort of strictly increasing still, but I get a exponential curve on like the motion in between the points. That way, sort of like the halfway point and, other things like that make sense and are not sort of weirdly lopsided. And we'll see if that we'll just hear it. We'll hear it and we'll decide if it's a better effect or a worse effect, or if, what the comparison is. So let's go do that. Okay. So it turns out that the difference there is a lot easier to hear if you test it over a really wide range. So I had to fiddle with the range of the sounds I was using to hear it. But there is a pretty big difference, at least to my ear, once I figured that out. It kind of makes sense, right? If you're using a linear interpolation, a straight line is a pretty good approximation for an exponential curve when both points on the exponential curve you're looking at are very far to the right, because that exponential curve just is closer and closer to a vertical line over time. But if you start from something fairly small and then move out towards larger values, you can kind of hear the difference more clearly. There's a bigger difference between the straight line and the curve when it spans a wider range of values. So I put it over a pretty wide range of values. I think it spans like 4 octaves. Here's what the linear pitch bender sounds like. And here's what it sounds like when I convert the frequencies out of the exponential space and then with a log, and then interpolate and back into the exponential space afterwards. I don't know. I think that's pretty interesting. It's definitely very much in the realm of subjective experience, which of those sounds like a linear thing, because your ear is not going to be very useful for determining what a linear change in pitch even means. But the second one is the one that sounds linear to me, so I feel like I like being able to, I like at least having the knowledge that that's like how you can control that and get that more precise. So that's cool. Next up, I'm going to move on to playing a little bit with generating white noise and then using filters to alter the sounds of existing samples. So like the idea is first we make some white noise, and then we can do a low pass filter or a high pass filter to adjust the pitch of those. So I want to see if I can pull those things off. These high pass and low pass filters are fairly technical aspects of the sort of discipline of signal processing and audio processing. And actually, I've been studying it, but the math that justifies the algorithms I used doesn't totally make sense to me yet. I get the very general principle, but I'm still working on it, and writing this code has sort of helped me make a little more progress on digesting the math, but I'm still not all the way there. So there's only so much of this I can explain, but I'll give you a couple of points of what this stuff's all about as far as I'm able to understand it. So first of all, the basics are a low pass filter is something that takes in a signal and sort of keeps the low frequencies as they are, and at a certain cutoff point it sort of turns down all the higher end frequencies. So it makes a thing sound like the higher frequency sounds in a signal will be quieter after you use that. And then a high pass filter just does the opposite, right? It turns down the frequencies that are lower pitch in a signal. So they're kind of like a greater than sign and less than sign. They filter in opposite sides of a particular cutoff point. For these particular algorithms, there's not the only way we could do it, but it's just the ones that are super simple based on a single loop pass. There's no fast Fourier transform that we have to do to make this kind of stuff work yet. So I just went with it. It's also there's pseudocode on Wikipedia, even though it's a little bit maybe annoying or tricky to digest. Even though there's pseudocode, I was able to muddle through it and sort of debug it, toy with it to make it work. So in essence, what these are doing is the low pass filter kind of is like blurring the signal. You can imagine taking like any kind of blur effect that you could apply to an image, and instead of applying to an image, it's just this one-dimensional series of samples, and it's kind of blending the sounds together. And what that does is any quick, fast changes in the signal get lost. They get kind of blurred over, but the general trends stay intact. So areas that are more up stay up, areas that are more down stay down. Like the general shape stays the same over long periods of time, but the quick changes get kind of blurred out. And then the high pass filter is trying to have the opposite effect by applying a delta every time. So it looks at the input signal, it sees the delta between samples, and it goes to add that delta into whatever the output sample is at, and then it decays it. So what that means, what sort of happens over time, is general trends get sort of decayed away. So if it was generally high or low for a portion of time, that will sort of decay to zero over time, and you'll lose those low frequency changes. But the immediate change gets preserved because the delta gets added in directly. So that's how it generally works. The exact math on how you specify the cutoff frequency and turn that into the blending factors, that's the part I can't really help you understand any better than like what's on Wikipedia. I did a little bit of algebra there to like debug it because I was a little confused. I wasn't getting the right results, and I was not quite able to like read the Wikipedia math. It doesn't spell out the steps as much as I think it should for people who are, new to the topic. But, if you sit down and work the algebra yourself, I think that they've got it right there. It's a little bit confusing, but it looks like you can work out the right thing to do from them, even if you can't fully understand the way the math is justified. So with these filters, we can make some sounds. So first of all, I've got this white noise sound, and I didn't really comment on how I generated that, but it's just a goofy little pseudo-random number generator. We'll put in a better one later. But for now, I use that goofy little pseudo-random number generator that's sort of like a lightweight PCG thing to generate white noise. Like it sounds like this. With a low pass filter keeping the lower pitches, it sounds like this. On the other end, with a high pass filter, we get this. And then if I use both at the same time, I can sort of select a range and emphasize the pitches in that range and let the pitches on both sides decay away or sort of be turned down, and I can sort of select a sort of small range of tones, which ends up sounding like this. And I like that quite a bit. It sort of sounds like the beginning of an ocean sound to me or something. So it's giving me hope that there's a lot of different sound effects that could be generated in this simple way over time. Okay, so next thing I want to get to is what I call like a sparkle effect, or another way that I'm sort of thinking about in my head is just like a particle effect for sound. And what I'm thinking of is just I want to be able to create a bunch of little sounds because I have these methods for sort of generating singular sounds at a time, and I kind of want to generate a whole bunch of them to create an effect that is the sum of lots of little effects, so like a sparkle effect of some kind. I'm going to give that a shot. Okay, I had a lot of fun building that there, but it doesn't really feel like it's turning into some sort of reusable, generally applicable tool. It's more like just a handwritten thing specifically applicable to the effect I was getting here. And if I was going to go do a different sound effect, I might need slightly different parameters, slightly different random generation techniques. There's just not like I didn't like tap into something that is super reusable yet. So I don't know that it makes a lot of sense to keep going down that road right now. I think that maybe what I should do is take this notion I have and stick it on a to-do list, stick it back in the back of my head, and see if I come up with something better later on when I've maybe had some other aspects of the space, have had some time to sort of make sense and click in my head better, and I just let this idea cook for a little while. Maybe I'll have a better version of it in mind the next time I bring it up. So whatever is going wrong with it, I can't quite diagnose, but it's not super critical, so I don't need to keep like consciously putting work into this. I can let this one sort of be a back burner problem. I did manage to make a kind of fun sound effect out of this. So here's the sound effect I made, which I'm dubbing the time machine effect. I still have 2D positional sound on my to-do list, but I think I'm going to hold on to that to-do and leave it for a future arc that revisits this code. And the reason for that is mostly I'm just seeing a lot of code sitting around now that I need to clean up first anyways. There are certain things that are not quite clicked in with the API that maybe need a pass. So there's a number of issues that I've built up. Some of them are to-dos in my notebook, some of them are to-dos that I've written in the code, and some of them are just in my head. And I'm feeling like it's kind of reaching a critical mass where I need to get sorted out what's hairy, what's cleaned up, what's in a good state, what needs more work. And I'm also kind of feeling like this arc has gone on for long enough at this point. I'm kind of losing steam for this particular topic personally. So I don't want to keep pushing myself to do this one while I'm kind of not able to bring my best to the challenge. So I'm going to wrap this one up next time, and then we'll do something new.